I left off with a 1 millisecond timer and input-output ports working. In the last couple of weeks, I did get time to poke around with it a bit more. I used timer TCA 0 for the 1 millisecond timekeeping. It looks as if the Type A timer is geared more toward output, and the Type B timer is geared more to input measurements. Of course, both seem to work as a basic 16-bit timer. But what I didn't look at was the RTC counter, as it seems to be clocked from the low-frequency oscillator, but I should have. This looks to be a perfect peripheral to keep a nicely timed program loop running. So I'm going to start by digging into the RTC Timer module. It can generate up to 3 interrupts, so instead of having to keep time with software, can just let this RTC module keep track of it, with some limitations. Let me fire up the MCC and see what it looks like. Right now I have TCA 0 supplying the 1 millisecond time interval, but I'm not using an interrupt, so I'll just leave TCA 0 as it is for now. On the list of device resources, I'll go down to the RTC and add it. Open up all the menus for the options. Leave the name as it is. Might as well leave it enabled. Defaults to the internal 32 kHz oscillator. That's just what I want. Just going to use the period setting here, and I'll set it to 1 millisecond. So every 1 millisecond, the RTC counter should overflow. And I will make sure the interrupt is enabled for the overflow. I'm going to enable the periodic interrupt timer. It can be set to interrupt from 4 to 32,768 RTC clocks. The prescaler for the RTC clock is set to divide by 1. So if I select 32,768 RTC clocks, that should give me an interrupt about every 1 second. I'll enable the interrupt for this as well. Now for this, I'm going to set 2 more pins to output. I'll put in a couple of 603 jumpers on my PC board to make it easy to test with the scope. Actually see what kind of timings I get. I'll set PA6 and PA7 to outputs. Give them a name that I can remember. Generate the code and close out the MCC. Of course, the first thing I'll take a look at is the rtc.h header file it created. So we have 3 functions to set a callback function for the interrupts. I'll need to use the setOVF and the setPIT ones, and it takes a function pointer with no parameters and a void return type. Now I do like to take a look at the .c file as well, if for nothing else to get a better idea of what the configuration registers look like. The period register is set to 31, so 32 kHz clock or thereabout, and if 0 is included in the register, should be close to a 1 millisecond interrupt. I need my 2 callback routines. I'll call the fast one timer_1ms, and I'll just toggle one of the output pins. For the 1 second, I'll just toggle the other output pin. Put the function prototypes in place. I'll just copy the function names from the rtc.h file. Put it right before the main program loop. This is the 1 millisecond one, so it gets timer_1ms. Almost forgot to include the rtc.h header file. Then I'll add the period interrupt timer callback. And then compile it, and no errors. But I've still got to turn on global interrupts for it to work. I'll have to look that up. Okay, had to hit the XC8 user's guide for the AVR built-in functions list. I don't think I ever would have guessed that one. There's supposed to be a macro called EI, but I'm going to use the full built-in function name. Here's the signal at the test 1 PA6 port pin. That's pretty close, it looks like. A little under 1 millisecond between interrupts. Would be double the 522 cycle frequency. So running 1.044 kHz, that's less than 5% error. I think that's pretty good for the 32 kHz oscillator. Let me see if adding one to the period register gets me a little closer to the 1 millisecond mark. I'll just update it in the MCC generated file for right now. Yes, that's very close. About 1.014 kilohertz. So just a bit under 1 millisecond. Less than a 2% error. Of course, changing the period register will not affect the 1 second timer. Now here's the signal at the test 2 PA7 port pin. Frequency counter in the scope doesn't work below 15 Hz, so all I have is the cursor measurements. Certainly not that accurate, but the 1 second interval seems to be in the 980 millisecond range. Now if I needed closer than this, it would be time to move to a crystal oscillator. This 32 kHz oscillator is not going to be that stable over voltage or temperature. That will be something to test, I guess. Of course, editing anything in the MCC generated files will bring problems. The MCC seems to do a pretty good job of warning when things have been changed, but there's no need to even mess with that. I'll go back into the MCC. With the Easy Setup tab, all I have is the time setting. I'll go to the Register tab, and down at the PER register, I'll change it to 20 hex. I'll generate the code again. Can see in the RTC.C file, the PER register is the 20 hex value. And it updated the time in the Easy Setup to 1.031 milliseconds. Let me replace the TCA timer with my new 1 millisecond function. I'll create a software flag to replace the TCA interrupt flag. I will set the flag in the 1 millisecond function. And in the run loop, I will test for it being set. When it is set, I will clear it and run the rest of the code just like it was. I can't tell any difference. There's bound to be a few milliseconds difference, as I'm pretty sure the high frequency oscillator is a bit more accurate than the 32 kHz oscillator. But now, TCA is available to use for other things. Now that the program timekeeping is being done with the RTC timer, let's put TCA to work doing something else. Going to go to the single slope PWM mode, and I want channel 1. The reason I want channel 1 is from this table can see that the TCA waveform output 1 is connected to PA1, and that is the pin I have the LED 1 connected to. I'll set it to 50% duty cycle, but I haven't set the PWM resolution yet, so let me do that. I'll go to the Register tab and move down to the PER register. This register will set the PWM resolution. I'll set it to 7FF, that will give me 11 bits of resolution, way more than is needed. It will also keep the PWM frequency around the 1 kHz range with the TCA clock set the way it is. Then have to reset the duty cycle after changing the PER register. For some reason, the TCA module doesn't show a channel 1 output. Of course, that's the one I want to use. I did check the errata sheet and didn't see anything about channel 1 not working. So maybe it's just a bug in the code configurator. I'll generate the code and see what happens. I'll take a look at the TCA0.h file and see if anything has been added. Nothing stands out. Sure don't see anything for setting the compare 1 register. I'll take a look at the TCA0.c file. So I have the name of the compare register that was set to 50% duty cycle. The double buffer of that register is the one I will be updating though. So I'm going to fade the LED in and out with the TCA channel 1 PWM. I will adjust the PWM value every 1 millisecond, and with a range of 0 to 2047, should take about 2 seconds to fade the LED, so 2 seconds to go up and 2 seconds to go down. Now I'm using the channel 1 compare buffer here instead of writing directly to the compare register. If I remember correctly, this buffer value will transfer to the compare register when the timer count register equals 0. So hopefully no glitches in the output. No errors, so let's see what it looks like. Yeah, that's probably around 2 seconds. It's a good sign when it does what you think the code should make it do. Since channel 1 seems to be working fine, it not showing up in the TCA 0 pin table sure seems to be a bug with the MCC. Enabling channel 0 or channel 2 seems to show up just fine, or trigger a warning to set the pin to output. No big deal, as it seemed to generate the code just fine. But if I had PA1 pins set to an input, it wouldn't have worked and no warning given about the output direction. Not the first bug I've run across in the code configurator, and I'm sure it won't be the last. Thank you for watching.